Dun 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 da da dun 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 da 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 dun 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 da 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 dun da da dun da dun 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 dun. Today's Jeopardy contestants are Winnie, Billy, and Raj, presented to you by host Benny.
Alrighty, Winnie, you have the honor of being the last person to end off tonight's show. Which category will you choose?
Long and annoying things are 500.
Alright, as a reminder, you have 10 minutes to answer the question. Please wait as the system flips to the question. It's a daily double! Winnie, you may be in last place currently, but if you wager the right amount, you can turn this game completely over.
Billy has 2,700 points, and Raj has 3,000 points. I will wager all the points I currently have.
Wow, contestant Winnie just has wagered all 1,700 over points. How spicy. Alright, here's your question. Graph the following polynomial function, p of x equals 5x to the 6th power plus 13x to the 5th power minus 14x to the 4th power minus 47x to the 3rd power minus x squared plus 32x plus 12. The clock starts now!
Oh shoot, I should have listened to Mr. Cheng in class.
Remember, Winnie, you can still phone a friend if you get stuck.
Alright, I'll just do that. Beep 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 beep.
Who the hell are you?
I'm in Jeopardy. I need to answer these questions correctly to win.
Okay, what's the question?
Graph the following polynomial. P of x equals something, 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 something. I don't want to say.
Oh, Frank, let me get a piece of paper.
Hello folks! So in this video, I'm going to be explaining how we factor / graph higher degree polynomial functions. But before I do that, I'm going to introduce a couple of theorems that I feel like would be very helpful in helping us understand the process, why it works, how it works, stuff like that. So if we're trying to graph a polynomial function, what is one piece of information that would be very valuable for us to know? Well, it would be very helpful if we knew what the roots were, because if we knew what the roots were, we would be able to plot them onto the graph, and that would give us a general idea of what the graph's supposed to look like. So let's do that. I'm sorry, I'm speaking really quickly. We know that in order to find the root of an equation, we're going to have to set y equal to 0. So p of x equal to 0. We know that some number when plugged in for x is going to give us this output. Let's refer to this number as b. Again, what p of b equals 0 means is that when I plug in a b for x into this equation, the output that I end up getting is 0. We know that b is a root. We're used to going from factor to root, but not so much root to factor, and this is what I mean. Let's pretend we have the factored equation x minus 2 times stuff is equal to 0. Well, if we used the zero product property, we would know that one of the things being multiplied together is going to have to be equal to 0. So let's pretend x minus 2 is equal to 0. If we add 2 onto both sides, we get x is equal to 2. That's the corresponding root to this factor. And in this case, we know that, okay. We know that b is a root, so x equals b. We know that that's a root. What's the corresponding factor? As you can see, we're kind of working backwards here. So we know that x minus b must be a factor, because if we plug b in for x right over here, we end up getting b minus b, which is equal to 0. And this thing that I just explained to you actually has a name. It's called the factor theorem, which states that x minus b is a factor of p of x, and p of x refers to any polynomial function if and only if p of b is equal to 0, which is exactly what we proved right over here. For this next theorem, I'm going to start off with the example equation y is equal to 2x plus 2 times 2x plus 3. If I were to rewrite this in standard form, I would have to multiply everything out. So 2x plus 2 times 2x plus 3 gets me to 4x squared, 6x, 4x, 6. So standard form would be 4x squared plus 10x plus 6, but I actually don't care about what's in the middle. I only care about my leading term and my ending term. I'm going to refer to the 4 as my leading coefficient. And I'm going to refer to the 6 as my constant. Where do I get the 4x squared from? Well, if we look at the generic rectangle, we can see that 4x squared comes from multiplying 2x by 2x, and 6 comes from multiplying 3 by 2. So the general observation that can be made here is that the leading coefficient is the product of the x terms, and the constant is a product of constant terms. If I were to ask you this question, is 3x plus 4 a factor of 4x squared plus 10x plus 6? Well, hopefully your answer would be no, because we know that there isn't an integer number that we can multiply 3 by that will get us to 4, and there also isn't a number that we can multiply by 4 that will get us to 6. So this is not a factor. What if instead of 3x plus 4 we had 2x plus 4? Well, this still wouldn't work out, because even though 2x can be multiplied by 2x to get us to 4x squared, the 4 part still doesn't work out. So even if there's only one number that doesn't satisfy the requirements, that's enough to make it not a factor. Sad. Okay, so what I just explained to you guys actually has a name. Again, it's called the rational root theorem, and this states that ax minus b is a factor of p of x, which refers to any polynomial function if a is a factor of the leading coefficient and b is a factor of the constant term. So, for example, we know that 2x plus 3 is a factor of 4x squared plus 10x plus 6, because 2 is a factor of 4 and 3 is a factor of 6. And yeah, that checks out. What is another piece of information that we can draw out of the rational root theorem? We know that the corresponding root to the factor ax minus b is x equals b over a. And to explain why this is the case, because of zero product property, we have to set the factor equal to 0. We add b onto both sides. We get ax plus b. I mean, not ax plus b. Ax equals b. You divide both sides by a. End up getting x is equal to b over a. That's our corresponding root. Now that we know what the factor and rational root theorems are, we can finally start working on the actual problem. Hooray! Okay, so I've written out this step-by-step guide on how to factor like a cool kid. Step number 1 says to list out all possible roots using what we know from the rational root theorem. We know that the roots are going to be in the format b over a, where b is a factor of the constant and a is a factor of the leading coefficient. In this case, the constant is 12 and the leading coefficient is 5. So I've listed the factors for both of these numbers, and I've also listed out all of the possible roots. There are 24 in total, which might seem like a lot, but if we consider the fact that we started out with an infinite number of possibilities, 24 actually isn't that bad. Okay, moving on to step number 2. Plug in possible roots into equation as x, and you know you've found the root when y is equal to 0. State the root's corresponding factor. So I'm going to plug in 2 for x because I like the number 2. When I plug in 2 for x, I end up getting p of x is equal to 208, which is not 0. this tells me that 2 is not a root of this function. But if I plug in 1 for x, I end up getting 0 as my output. This means that 1 is a root, and the corresponding factor would be x minus 1. And I've already discussed the factor theorem and how that works, so I'm not going to go into detail again. So it says in step 3 to divide p of x by the factor that we just got from step number 2. So p of x divided by x minus 1 gets me to 5x to the 5th power plus 18x to the 4th power plus 4x cubed minus 43x squared minus 44x minus 12. Step number 4 says that we have to continue factoring this until we get to a quadratic. So we have to repeat this entire process all over again. Luckily for us, the roots for this equation are going to be the exact same as, or the possible roots for this equation are going to be the exact same as they were for our original polynomial function, because the leading coefficient is still the same. It's still 5, and 12 and negative 12 have the same factors. So the possible roots are still going to be the same. If we plug in these numbers into this equation as x, we end up figuring out that p of negative 2 is equal to 0. So the corresponding root, the corresponding factor would be x plus 2. Now we have to divide this equation by x plus 2. We get 5x to the 4th power plus 8x cubed minus 12x squared minus 19x minus 6. We have to continue factoring because we're not yet at a quadratic. Does that even make sense? I don't even know. I don't know how to use grammar anymore. Okay, let's factor this. So the possible roots for this equation are going to be different because we have negative 6 as our constant now. Factors of negative 6 are positive and negative 1, 2, 3, and 6. So the possible roots are going to be positive and negative 1, 2, 3, 6, 1/5, 2/5, 3/5, 6/5. Okay, so now that we have all of our possible roots, all we have to do is plug them into the equation one by one to see which one results in an output of 0. P of negative 2 ends up equaling 0. So we know that negative 2 is a root, and its corresponding factor is, once again, x plus 2. If we divide this equation by x plus 2, we end up getting 5x cubed minus 2x squared minus 8x minus 3. Okay, so we have to factor this down even more because, like I said at first, this is not a quadratic. So the possible roots are going to be different again because we have a different constant this time. We have negative 3 as our constant, and the factors of negative 3 are positive and negative 1 and positive and negative 3. So our possible roots for this equation are going to be positive and negative 1, 3, 1/5, and 3/5. I can't even, that is really ugly. Okay, so let's test these roots out. If we plug in -3/5 into the equation as x, we end up with 0, which tells us that -3/5 is a root. But how do we find its corresponding factor? There we go. Okay, so we can write the corresponding factor as x plus 3/5, because if we were to plug in -3/5 in as x, that would be equal to 0. You know, that would make this equal to 0. Okay, but I'm not going to do that because we know that in a later step, we're going to have to divide our original polynomial by this, and I don't want to deal with fractions because that's just going to make it very confusing, and that's going to make my life a pain in the ass. So I'm going to rewrite the factor as 5x plus 3, and I'm going to explain to you guys how I got here. We know that the root is written in the format b over a, so we can refer to -3 as b and +5 as a, and we know that the factor is written in the format ax minus b, so we plug in a here, we get 5x minus b is -3, so 5x minus -3, which ends up being 5x plus 3. So yeah, that's our factor. If we divide this equation by 5x plus 3, we end up with a quadratic x squared minus x minus 1. Woohoo! So we're finally left with a quadratic, and we know how to factor quadratics already, so this should be relatively easy. But wait, is this even factorable in the first place? Well, to test this out, we can use the discriminant test. I'm trying to speak as quickly as possible because I do not want to make this video half an hour long. But it probably still is going to be like an hour long or something. I don't know, whatever. Okay, so the discriminant test for factorability states that if the result from b squared minus 4ac is a perfect square, then the quadratic equation is factorable. But if it's not a perfect square, then the quadratic is not factorable. So let's apply the discriminant test on this function that we currently have in front of us. So -1 squared minus 4a is 1, c is -1, that ends up being +1. -4 times -1, +4, ends up being 5. 5 is not a perfect square, so we know that x squared minus x minus 1 cannot be factored. But since this discriminant is still positive, we know that this quadratic does have 2 real roots, even though they might not be integer roots. So if we use the quadratic formula, b squared minus 4ac all over 2a. If we use the quadratic formula, we end up getting 1 plus or minus square root of 5, because we already figured out what the discriminant is, over 2. So our roots are going to be at 1/2 plus the square root of 5 divided by 2, and 1/2 minus the square root of 5 divided by 2. These are complex conjugates. Haha, fancy vocabulary term. These are going to be our 2 roots. I'm going to rewrite this as 1.618 and this as -0.618, just to make it easier for me to locate these points on the graph. Okay, let's sum up our findings. What are our factors and what are our roots? So our factors, I'm going to highlight them. There's x minus 1, x plus 2, 5x plus 3, and x squared minus 1. Okay, so the factored form of p of x would be x minus 1, x plus 2 times x plus 2, which is the same as x plus 2 squared, 5x plus 3, x squared minus x minus 1. Okay, that's the factored form of this polynomial function. And what are our roots that we can draw out? Well, x is equal to 1 here, x is equal to negative 2, x is equal to negative 3/5. By the way, I'm using the zero product property to solve this. And this is 1.618 and negative 0.618 because I solved it using the quadratic formula. This is where I'm going to introduce our final theorem. It's called the fundamental theorem of algebra. Very fancy name. Which states that an nth degree polynomial has an n number of roots. Well, what does this mean? We know that we have a 6th degree polynomial because if we look at the original equation, as you can clearly see, it says x to the 6th power. So obviously, it's a 6th degree polynomial. Okay, so if we have a 6th degree polynomial, that means that we're supposed to end up with 6 roots, according to this theorem. Let me count our roots real quick. We have 1, 2, 3, 4, 5. Wait up! We only have 5 roots, but we have a 6th degree polynomial? Like, how does that match up? Wait up. Did I make a mistake somewhere? No, I did not, because as you can see here, we're actually squaring the x plus 2 part. So this root, x is equal to negative 2, actually comes up twice. We can also say that its multiplicity is 2. The multiplicity of every other root would be 1 because they only show up once. Because the rest of these are linear factors. I mean, x squared minus x minus 1 isn't a linear factor, but you still get like 2 roots out of that anyways, so there wouldn't be a repeated root. Okay, now that we've cleared up that confusion, let's actually graph this thing now, because I know that's what we've all been waiting for. So we know that this is a 6th degree polynomial. Oh, we also have to find out what the y-intercept is. The y-intercept is going to be 12. If you plug in 0 for x into the original equation, you end up getting 12 as your answer because, 0 to the 6th power is 0. You multiply 0 by 5, that ends up being 0. That idea applies for every other term that has an x in it. The only term that doesn't have an x in it is the positive 12 at the end. So obviously the y-intercept is going to be 12. That's just a little shortcut that you can use. We also know that we have a positive leading coefficient, which means that the graph is going to have a positive orientation. So the graph ends up going upwards. It ends off going upwards, like on the right side of the graph. If that makes sense. Whatever, I'm just gonna graph it. If it doesn't make sense now, it's gonna make sense later. Okay, so we graph this. We know that our roots or our x-intercepts are at x is equal to 1, -2, -0.6, and -0.618 are literally right next to each other. I don't know who came up with this problem. Cough, cough, cough. But that's literally screwed up. 0.618. I know none of the scaling is accurate, but we're just not going to worry about that. So x equals 1, x equals -2, x equals -6, -0.6, 0.618. Okay, and then we have 1.618. We know that the graph ends up going upwards towards positive infinity because it has a positive orientation. So I'm just going to draw that part first. Okay, the y-intercept is at 12. I'm actually going to label that also. Since this is an even degree polynomial function, it's best for us to assume that the graph is going to end and start off in the same direction. So if it ends up positive, it's going to start positive as well. So okay, it's gonna go down until it hits it's gonna go down until it hits x equals -2, and we know that this factor is squared, which means that it bounces off at this point. This happens for any factor that's raised to an even power. It bounces off. It forms a little parabola shape at the root. Whereas for linear factors, it just goes straight across. Okay, so -0.618. It's going to go straight across. It's going to also hit -0.6. It's going to go straight back up. Blah, blah, blah. Hit the y-intercept. Go down again to hit x equals x equals +1. Then it's going to go up again to hit 1.618. And this is what your graph should end up looking like. It actually looks really bad on my screen, but I promise the one that I drew in my notebook looks like 10 times better. So, yeah.
I did it.
The final answer?
Yes.
Okay, allow me to use our best friend Decibel's graphing calculator. Correct! Congratulations, Winnie. You just won yourself Mr. Chang's approval.
Screw you, Mr. Chang. I don't want your approval. Please don't say that. I really kind of want your approval. Michelle's already decided, so use Michelle's fault.